4.2 light-years away, a planet sits in the warm zone of a red dwarf, and every signal we have screams that something is wrong. Proxima B orbits its star in 11 days. One side burns, the other side may have frozen its own air. The star throws flares so violent that one of them, in 2016, brightened the sky 68 times in seconds. We will visit the killing dose, the missing magnetic shield, the stellar wind that hits like a hurricane, and the laser fleet humans are designing to fly there. If you want the real verdict on the closest Earth-like world, hit subscribe. Strap in. We launch now. Pull up the navigation display. The target is a red dot, fainter than anything you can see with the naked eye, sitting 4.2 light-years from the launch pad. That distance sounds small until you do the math. Light, the fastest thing in the universe, takes more than 4 years to cross it. Our fastest spacecraft, Voyager 2, would need around 75,000 years. We are not driving across a continent. We are crossing an ocean of vacuum so wide that a single photon gets bored on the trip. Around that red dot, in 2016, a team led by astronomer Guillaume Anglade-Escud announced a discovery that broke the internet for a week. There was a planet. It was roughly the mass of Earth. It was sitting in the warm zone where liquid water could, in principle, exist on the surface. They called it Proxima B. Within hours, every space agency on the planet started rewriting its long-term roadmap. Here is why this single rocky world matters more than any of the thousands of other exoplanets we have found. It is the closest one. If humanity ever sends a probe to another star, this is almost certainly the destination. Nothing else is even in the running. The next candidates are decades farther away in light travel time, and decades matters when your power source is a sliver of plutonium decaying in deep space. So the mission planners got to work. The probe could not be a typical spacecraft. A school bus-sized robot with chemical rockets would arrive sometime around the year 75,000 of our era, which is a long time to wait for a postcard. The math forced the engineers into something stranger, something smaller than a smartphone, something accelerated by light itself, something that would scream past Proxima B at a fifth the speed of light, take pictures during an 8-minute flyby, and then beam those pictures back across more than 4 years of empty space. That is the mission. That is the only mission anyone has seriously proposed that arrives within a human lifetime. Every other concept dies on the launch pad of basic physics. And the closer you look at the destination, the more you realize the engineers may be sending those probes toward a graveyard. Because Proxima B is not the friendly twin of Earth that the press releases suggested. The star it orbits is a flare star, one of the most violently active stars in our local neighbourhood. The orbit is so tight, the planet is almost certainly tidally locked. The atmosphere, if it ever existed, has been hit with 7 to 16 times the cumulative high-energy radiation that Earth received over the same span. And those numbers come to account for the superflares. Every assumption that made Proxima B sound habitable in 2016 has been quietly eroded by the data that came afterward. The habitable zone is not the same thing as a habitable planet. A planet inside that zone, around a star like this one, may be the most hostile rocky surface within 10 light years. The briefing starts with the basics. Then we go to the flares. Then we go to the missing magnetic shield. By the time we reach the laser array, you will understand why every engineer on this mission has the same expression on their face. Set the first waypoint. The orbit comes next. Look at where Proxima B sits in its orbit. If you drop the system onto a desk, with the star at the centre of a dinner plate, the planet would be circling about a fingertip's width from the surface. The actual number is 0.048 astronomical units. For comparison, Mercury, the closest planet to our own star, sits at 0.39. Proxima B is more than 8 times closer to its star than Mercury is to ours. That tight orbit gives the planet a year that lasts 11.2 Earth days. A child born on Proxima B at our launch would celebrate its first birthday before our ship had cleared the asteroid belt. By the time we crossed the heliopause, that child would be older than most pet dogs back home. The reason a planet can orbit this close and still sit in the warm zone comes down to the star itself. Proxima Centauri is a red dwarf classified as M5.5v. It puts out roughly 1/1000th of the light our star produces. It is a candle compared to a stadium spotlight. A planet orbiting a candle has to sit very, very close to feel any warmth at all. That is the only reason the surface temperature on Proxima B might allow liquid water. The planet is hugging the heater. The cost of that hug is brutal. The closer a small planet sits to a star, the stronger the tidal forces stretching it. Tidal forces scale sharply with distance, and at 0.048 astronomical units, those forces are enormous. The same physics that makes Earth's ocean bulge toward the moon is happening to Proxima B's entire body, except with a force budget thousands of times larger. Tidal forces do something specific to small worlds in tight orbits. They drain rotational energy. They slow the planet's spin until something locks. We will get to what locks in the next waypoint, but understand the mechanism here. Every time Proxima B tries to rotate, the bulge raised by the star drags against the rotation and bleeds energy away. Over millions of years, the spin slows. Over hundreds of millions of years, it stops doing what Earth does. There is one piece of good news in all of this. The orbital period of 11.2 days is stable. We measured it through the radial velocity method, watching the star wobble back and forth as the planet tugs it. The wobble is tiny, and Glada Eskard's team had to stack years of data to pull the signal out of the noise. But the signal is real, the orbit is confirmed, and the planet sits there, every 11 days, looping its star at a speed that would carry it from Los Angeles to New York in under a minute. Picture that for a moment. A whole year, sunrise to sunrise, in less time than a lunar phase, 11 days from spring to summer to fall to winter, except none of those seasons exist, because the planet does not tilt the way Earth does. Most likely, it does not tilt at all. Most likely, it does not really turn. The next waypoint is the worst news yet. One face of this planet may have been staring at its star for billions of years. Tidal locking. That is the term the mission planners use, and on Proxima B, it is almost certainly what happened. The planet's day became equal to its year. Every 11.2 Earth days, Proxima B makes one orbit, and during that same span, it rotates exactly once. The result is that one hemisphere always faces the star. The other hemisphere never does. There is no sunrise on Proxima B. There is no sunset. If you stand on the day side and walk in any direction except toward the star or away from it, the star stays in the same spot in the sky for the rest of your life. If you stand on the night side, you stand in darkness so absolute that the only light comes from stars and, occasionally, from the violent aurora caused by your star's plasma, slamming into whatever atmosphere remains. This setup creates two completely different worlds glued to the same planet. The day side absorbs constant radiation. Without an atmosphere to redistribute the heat, the substellar point, the spot directly under the star, becomes a baking circle of rock. The temperature of that spot depends entirely on whether Proxima B has air. With no atmosphere, the day side could approach temperatures that boil water. With a thick carbon dioxide atmosphere, the heat could spread, but the surface still stays uncomfortably warm. The night side is the mirror image, with no incoming radiation, no rotation to bring warmth around, and no internal heat sources beyond the planet's natural radioactive decay. The night side approaches the temperature of deep space. Atmospheric models suggest the dark hemisphere of Proxima B could fall well below the freezing point of carbon dioxide itself. That matters, because if the planet's air contains carbon dioxide, that air starts snowing onto the night side as dry ice. This is a process scientists call atmospheric collapse. The atmosphere literally falls out of the sky on the cold side. Every gas molecule that drifts across to the dark hemisphere has a chance of freezing onto the surface. Once frozen, it stays there. Over geological time, the entire atmosphere can migrate from the day side to the night side, where it sits as ice, never to return. There is a possible escape from collapse, and it depends on something the mission planners cannot yet measure. If Proxima B has a thick enough atmosphere, the winds might transport heat from the day side to the night side fast enough to keep gases from freezing. Climate models from teams at NASA Goddard and elsewhere suggest a layer of carbon dioxide thicker than Earth's whole atmosphere might do the job. The wind speeds in those simulations are violent. We are talking about jet streams that would shred any aircraft we currently build. If the atmosphere is thinner, the winds lose. The collapse happens. Proxima B becomes a planet with a baked day side, a frozen night side, and a thin layer of air clinging stubbornly to a narrow band in between. That narrow band is where everything interesting happens. That is the only place where temperatures might allow liquid water. That is the only place a probe should image. That is also the strip where every bad thing about this star tends to hit hardest. The next waypoint is that strip. They call it the terminator. The terminator is the line on a planet where day meets night. On Earth, it is a moving boundary, racing around our planet at the speed of rotation, giving every spot on the globe a sunset and a sunrise. On Proxima B, the terminator does not move. It is a fixed ring, frozen in place forever, dividing the burning face from the frozen face. That ring is where every climate model points as the only zone where surface life might survive. The math is simple. The day side is too hot under the constant glare. The night side is too cold under permanent darkness. The terminator sits in between, where the star hangs forever just above the horizon, never rising, never setting. The temperature in this zone could, in theory, allow liquid water to pool on the surface. Picture standing there. The star fills part of the sky as a huge red disk. Bigger than our home star looks from Earth, because Proxima B is so close to it. The light is the colour of a deep sunset on Earth, redder, dimmer, but constant. There is no morning, there is no evening. There is just one perpetual late afternoon stretched out across geological time. The shadows never change length. Atmospheric scientists call this kind of world an eyeball planet. The image is direct. Looking down from orbit, you would see a circular ocean of liquid water under the substellar point, surrounded by a wider ring of habitable terrain at the terminator, surrounded by frozen wasteland on the night side. The whole planet looks like an enormous staring eye, with a warm pupil and a cold sclera locked in one direction forever. There are problems with the eyeball model. The first is that the terminator is narrow. The habitable strip on a tidally locked Earth mass planet might be a band only a few 100 miles wide. That is roughly the size of a single American state. All available real estate for surface biology compresses onto that one ring. The second problem is wind. The temperature difference between the day side and the night side drives the most violent atmospheric circulation any climate model can produce. Air rises over the hot point, races outward toward the cold side, sinks, and rushes back along the surface. The terminator strip sits directly in that flow path. Surface winds at the boundary could exceed 200 miles per hour as a baseline, with peaks higher during transient weather. The third problem is the weather itself. Where hot wet air from the day side meets cold dry air from the night side, you get permanent storm systems. Models suggest constant cloud banks, towering thunderstorms locked in place, and rainfall patterns that never shift. A single mountain range could create a wet face and a dry face for the entire history of the planet. There is something almost beautiful in the picture, and something deeply hostile. The terminator is the only spot we would aim a camera. It is also the spot most exposed to whatever the star throws at the planet. Because the star sits low on the horizon there, every flare, every burst of radiation, every coronal mass ejection slams into the terminator at an oblique angle that maximizes. Atmospheric penetration. which brings us to the next waypoint, and to the reason this mission keeps getting harder. The star itself. Proxima Centauri is classified as a flare star. That label sounds technical. It is actually a warning. A flare star is a star that erupts with sudden, violent bursts of energy on a regular basis. The bursts come from magnetic field lines twisting, snapping, and reconnecting in the star's outer layers. When they snap, they accelerate charged particles to a sizable fraction of the speed of light and dump huge quantities of energy into ultraviolet light, X-rays, and radio waves. Our home star does this too. Our home star does it rarely, and its biggest events are small compared to what Proxima Centauri does on a quiet Tuesday. The reason Proxima Centauri flares so violently comes down to its internal structure. Most stars, including our own, have a layered architecture. The hot core fuses hydrogen. Around the core sits a radiative zone where energy moves outward as photons. Above that sits a convective zone where hot plasma physically rises and cooler plasma sinks, transporting heat the way a pot of boiling water transports heat. Our home star has both layers. Proxima Centauri is too small to have that layered structure. It is fully convective. The entire interior of the star, from the core out to the surface, is one big roiling cauldron of plasma. There is no quiet middle layer. There is no stable region for magnetic fields to settle into. Instead, the magnetic field gets churned, twisted, and tangled across the entire body of the star, all the way down to the core. That tangling is what powers the flares. Every time a knot of magnetic field grows too tense, it releases. The release point is a flare. On a fully convective star, knots form constantly across the entire surface at every latitude and longitude. There is no flare-free region. There is no quiet patch where a planet might hide. The numbers are sobering. Photometric surveys using the MOST satellite caught 66 flares from Proxima Centauri in just 38 days of observation. That averages out to nearly 2 flares per day, every day, with energies ranging from 10 to the 29th ergs to 10 to the 31.5 ergs. Each of those flares would dwarf almost any flare our home star has produced in modern history. And those were the small ones. The Everyscope survey, run by the University of North Carolina, watches stars across the entire sky every 2 minutes. In 2016, it caught Proxima Centauri doing something far worse than its routine activity. The star produced a flare so bright it was briefly visible to the naked eye from Earth, despite Proxima Centauri normally being far too dim to see without a telescope. The star's optical brightness jumped by a factor of 68. It was, by the bolometric energy estimate, around 10 to the 33.5 ergs, roughly 10 times larger than any flare ever previously detected from Proxima Centauri. Astronomers call events like this superflares. They are not theoretical. They are happening on this exact star, near a planet we want to call habitable. A planet sitting at 0.048 astronomical units from a flare star this active is sitting inside the radiation budget. There is no shield of distance. There is no quiet decade where life could rest and recover. The star fires constantly, and one event in particular changed how every habitability researcher thinks about Proxima B. The next waypoint is that event. The date was March 24th, 2016. The Everyscope was watching as part of routine all-sky monitoring. For most of the night, Proxima Centauri sat at its normal dim brightness, a tiny red speck barely registering above the noise floor. Then, in the span of seconds, the speck became a beacon. The data captured the rise. Within 10 seconds, the star's brightness multiplied by a factor of approximately 1,000 at certain wavelengths. Across the broader optical band, the increase was roughly 68 times. For the first time in recorded history, Proxima Centauri became visible without optical aid from Earth. If you had been looking at the right patch of sky during those few seconds, you would have seen a star where, moments earlier, you saw nothing. The energy budget tells the rest of the story. astronomers estimate the bolometric energy of the event at 10 to the 33.5 ergs. That is roughly 10 times any previously detected flare from Proxima Centauri and about 30 times any optically measured one. For comparison, the 1859 Carrington event, the largest solar storm in modern human history, released around 5 times 10 to the 32 ergs. The Proxima superflare beat that by a factor of roughly 6. The Carrington event hit Earth. It set fire to telegraph offices in Boston. It made auroras visible in the Caribbean. Earth has a thick atmosphere, an active magnetic field, and a comfortable distance of around 93 million miles from its star. Proxima B sits roughly 4.5 million miles from its star. Take a Carrington-class event, multiply the energy by 6, and apply it to a planet over 20 times closer to the source. The radiation flux at the surface increases dramatically. The team that analysed the event ran the photochemistry. They modelled what would happen to an Earth-like atmosphere on Proxima B under the documented flare rate of the star, including the superflare. The result was straightforward. The repeated flaring is sufficient to reduce the ozone of an Earth-like atmosphere by 90% within 5 years. Complete depletion of the ozone layer would follow within several 100,000 years. 5 years, that is the shelf life of the ozone shield on Proxima B under the actual observed flare rate of its star. After 5 years, 90% of the protection is gone. After geological time, all of it is gone, and the planet's surface receives the full ultraviolet beating from every subsequent flare without any chemical buffer. The single superflare in 2016, on its own, delivered enough ultraviolet light to the surface to be lethal to almost every form of life on Earth. The dose during that event, on an unshielded surface, was around 100 times the level required to kill simple, ultraviolet, hardy microorganisms. 65 times the dose needed to kill 90% of one of the most ultraviolet-resistant organisms ever identified, Deinococcus radiodurans, which can normally survive. Radiation that would liquefy a human. This was not a hypothetical event. This was one observed outburst, on one calm night, captured by one telescope. The team reported that Proxima Centauri produces flares of similar magnitude approximately once every 5 years based on extended monitoring. Once every 5 years, the planet gets hit again. Once every 5 years, the ozone budget restarts. The ozone budget cannot restart fast enough. Ozone is a form of oxygen with 3 atoms instead of 2, and on Earth it sits in a thin layer of the upper atmosphere where it absorbs the most damaging ultraviolet light from our home star before that light reaches the surface. Without ozone, the surface of Earth would be a sterilized rock for any organism that depends on DINA. Bacteria, plants, animals, every cell that uses the standard genetic code would lose its information faster than the cell could repair it. On Earth, ozone forms because ultraviolet light splits oxygen molecules in the upper atmosphere, and the freed atoms recombine into the 3-atom version. The cycle is steady. The ozone budget gets continuously replenished by the same starlight that occasionally damages it. The whole system is in chemical equilibrium, and any perturbation tends to return to the baseline within a few years. The Tilly team modelled this same cycle for Proxima B. They started with an Earth-like atmosphere, the same nitrogen-oxygen mix, the same temperature gradient, the same upper atmosphere photochemistry. Then they fed in the actual measured flare rate of Proxima Centauri, including the superflare frequency. The model failed within 5 years. The mechanism is straightforward. Each flare delivers a burst of high-energy radiation and often an associated stream of charged particles. Both of those inputs do something specific to the upper atmosphere. They generate nitrogen oxides, the same chemicals that depleted Earth's ozone layer in the late 20th century when industrial chlorofluorocarbons were destroying it. On Earth, the source was human industry. On Proxima B, the source is the star itself. Each flare event injects a pulse of nitrogen oxides into the upper atmosphere. Those nitrogen oxides catalyze the destruction of ozone. The ozone depletion happens fast, within hours to days of the event. The recovery takes years. Earth's ozone layer, after a single Carrington-class event, would need around a decade to rebuild. Proxima B does not get a decade. Proxima B gets, on average, about half a decade between superflares, and is hit by smaller flares almost daily. The result is permanent depletion. After 5 years of cumulative damage, 90% of the ozone is gone. The atmosphere never gets enough quiet time to rebuild. The damage outpaces the repair. There is a darker version of this story. The 5-year figure comes from the model that includes a continuous ozone replenishment cycle from the star's normal output. If the planet's atmosphere is thinner or chemically different, the ozone never reaches Earth like levels in the first place. Models running with carbon dioxide-dominated atmospheres show ozone production that is orders of magnitude lower. The carbon dioxide does provide some ultraviolet shielding on its own, but not at the wavelength that ozone targets best. There is also the question of complete depletion, which the Tilly team estimated at several 100,000 years. Geologically, that is a blink. If Proxima Centauri has been firing flares at this rate for billions of years, and the planet has had any kind of Earth-like atmosphere for any of that time, the ozone shield has been gone for almost the entire history of the world. Without that shield, the planet's surface absorbs the full spectrum of ultraviolet radiation from every subsequent flare, all the way down through the most damaging band. The wavelengths that destroyed Dina in seconds. The surface dose during the next flare, with no ozone in the way, comes next. There is an organism on Earth called Deinococcus radiodurans. Its nickname is Conan the bacterium. It can survive radiation doses that would liquefy a human in minutes. It can survive being dehydrated, frozen, and pumped to vacuum. It can survive direct exposure to ultraviolet light at intensities that would carbonize most other microbes. Astrobiologists love it because it is the closest thing Earth has produced to a life form that might handle the surface of a hostile alien planet. Conan the bacterium would die on Proxima B's dayside during the next superflare in roughly 30 seconds. The number that came out of the Howard Ward team's analysis is 65. During the 2016 superflare, would the ozone layer of Proxima be assumed to be absent, which the previous waypoint established as the realistic baseline, ultraviolet dose at the surface was 65 times larger than the dose required to kill 90% of a Deinococcus radiodurans population. 65 times. Not 65% above. Not 65% more. 65 times the lethal threshold for the toughest microbe Earth has ever produced. A planet's surface receiving that kind of dose repeatedly every 5 years is not a place where complex biology can establish itself. It is a place where even the hardiest known life form would be reduced to broken DNAR fragments inside a single flare event. The death does not come instantly across the whole planet. The dose depends on which side of the planet faces the star at the moment of the flare. Since Proxima B is tidally locked, that question has a permanent answer. The day side always faces the star. Every flare hits the day side directly. Every flare hits the terminator strip at a glancing angle. Every flare passes harmlessly above the night side. The day side then has been receiving lethal class ultraviolet doses every few years for billions of years. Any surface biology there has either gone extinct or never managed to start. The terminator strip, our previous candidate for habitability, takes a partial hit. The radiation comes in sideways through more atmospheric column, which absorbs more of the damage. But the column is not thick enough to drop the dose below the lethal threshold for Conan the bacterium during a superflare. Life at the terminator survives the small flares and dies in the big ones. The night side is the one place where ultraviolet radiation never reaches the surface directly. The whole bulk of the planet sits between the night side and the star. Whatever biology might exist on Proxima B, the only ultraviolet safe real estate on the planet is the half that sits in eternal darkness and freezing temperatures, where there is no light source for any photosynthetic process to begin with. This is the trap Proxima B's surface biology cannot escape. The half of the planet with energy for life has lethal ultraviolet. The half without lethal ultraviolet has no energy for life. The narrow band in between, the terminator, gets reset to zero every few years by a superflare that wipes the slate clean. Astrobiologists studying this situation tend to point underground or underwater as the only places life might survive. A few feet of rock or several yards of liquid water would absorb enough ultraviolet to drop the surface dose below lethal levels. But that is not life that the probe could photograph during an 8-minute flyby. The next problem is whether the planet has any atmosphere left at all. The stellar wind is the steady flow of charged particles that streams outward from any star. Our home star produces a stellar wind that carries roughly 1 million tons of plasma per second outward into space. That sounds enormous until you consider how much space the wind has to fill. By the time it reaches Earth, the wind has thinned to about 5 particles per cubic centimetre. Earth's magnetic field deflects most of it, and what gets through powers the auroras and slowly chips away at the upper atmosphere. Proxima B sits in a different regime entirely. Estimates published in the Astrophysical Journal place the stellar wind density at Proxima B's orbit at somewhere between 10 and 1,000 times denser than the wind at Earth's orbit. The exact number depends on the phase of Proxima Centauri's 7-year magnetic cycle. At the quiet end of the cycle, the planet experiences a wind 10 times denser than what hits Earth. At the active end, with the star's magnetic field at full intensity, the planet sits inside a plasma flow up to 1,000 times denser. This is a hurricane. A continuous, never-ending hurricane of charged particles slamming into the planet from one direction every second for the entire history of the world. There is no calm period. There is no protected hemisphere. The whole day side gets hammered constantly. The pressure of that wind is what scientists call the dynamic pressure, and on Proxima B it is enormous. On Earth, the dynamic pressure of our home star's wind is balanced by the pressure of Earth's magnetic field at a boundary called the magnetopause. The magnetopause sits roughly 10 Earth radii out on the day side and acts as the planet's outer shield. Inside the magnetopause, the atmosphere is mostly protected. Outside, the wind streams freely. If Proxima B had Earth's magnetic field strength, the wind pressure at the planet's orbit would push the magnetopause down to roughly 2 planetary radii on the day side during the active phase of the star's cycle, that is so close to the surface that the upper atmosphere would sit outside the protective bubble. The wind would directly contact and erode the planet's air at altitudes Earth's atmosphere considers normal weather territory. If Proxima B has a weaker magnetic field, which the next waypoint will explain is the most likely scenario, the magnetopause gets pushed all the way down to the surface, or vanishes entirely. At that point, the stellar wind hits the atmosphere directly. Charged particles strip electrons off air molecules, accelerate them away from the planet, and drag them out into space along the wind's flow direction. Astronomers see this exact process happening on Mars in real time. Mars lost its magnetic field around 4 billion years ago. Since then, the solar wind has been stripping Mars's atmosphere, one molecule at a time, with measurable efficiency. The MAVEN mission documented around 100 grams of atmospheric loss per second in the modern era. Mars sits at 1.5 astronomical units from a star that produces a wind 10 times less intense than what Proxima B experiences. Proxima B, with no magnetic field, faces a wind potentially 10,000 times more aggressive than what stripped Mars. Whatever atmosphere it ever had, the stripping started early and never stopped. The next waypoint is the missing shield itself. A planet generates a magnetic field through a process called the dynamo effect. Deep inside the planet, molten conductive material, typically iron and nickel in the outer core, moves in a complex pattern of convection and rotation. The motion of charged material generates electric currents. The currents generate magnetic fields. The fields stretch out from the core, through the mantle, through the crust, and into space, where they form the protective bubble that shields the surface. Two ingredients are essential for a dynamo to work. The first is a liquid conductive layer somewhere in the planet's interior. The second is rotation. Without rotation, the convecting fluid does not organize into the helical patterns that pump out a global magnetic field. The fluid still moves, the heat still flows, but the magnetic output collapses to nearly zero. Proxima B is tidally locked. That is the previous waypoint. Tidal locking means the planet rotates exactly once per orbit, which translates to once every 11.2 Earth days. A normal day on Proxima B lasts almost 2 of our weeks. The rotational velocity of any point on the surface is about 1/8 what Earth provides. That slow rotation cripples the dynamo. The team led by Driscoll and Barnes published modelling work suggesting that tidally locked terrestrial planets around red dwarfs likely fail to generate strong global magnetic fields. The interior may still have a liquid outer core, the convection may still be vigorous, but the slow rotation prevents the fluid from organising into the coherent patterns required for a planetary dynamo. The likely outcome is a magnetic field that is either extremely weak, orders of magnitude below Earth's, or essentially absent. There is some possibility that the upper atmosphere, ionized by the star's radiation, generates its own induced magnetic field that provides limited shielding. Such a field would be far weaker than a core-driven one, and would offer almost no protection during stellar flares or coronal mass ejections. This combines with the previous waypoint in the worst possible way. The stellar wind density at Proxima B's orbit can reach 1,000 times Earth's. The planet's magnetic shield is potentially thousands of times weaker than Earth's. The product of those two ratios determines how much stellar wind reaches the atmosphere directly. By any reasonable estimate, the figure is millions of times what Earth experiences. There is one more wrinkle. Proxima Centauri has a 7-year magnetic cycle, similar in structure to our home star's 11-year cycle, but compressed in time and far more violent in amplitude. During the active phase of that cycle, the wind density spikes, the flare rate climbs, and any induced atmospheric magnetic field gets overwhelmed. Even if Proxima B has some marginal protection during the quiet years, it loses that protection regularly, on a timescale shorter than a human life. There is no shield. There is no quiet decade. The mission planners running atmospheric models have to assume the planet's air is exposed directly to the full force of the star's output, including the worst superflares. The only question is how long that air can hold on against the constant scouring. The answer, based on the cumulative numbers, is the next waypoint. Take everything from the previous waypoints and stack them together. A planet sitting 4.5 million miles from a flare star. A magnetic shield that ranges from extremely weak to absent. A stellar wind 10 to 1,000 times denser than Earth's. Repeated bombardment by ultraviolet light and X-rays at intensities our home star has not produced in modern history. Now ask the question every mission planner has to ask before designing the probe. Is there anything to image when we get there? The atmospheric stripping process works through several channels, all of them active simultaneously on Proxima B. The first channel is thermal escape. Ultraviolet and X-ray photons get absorbed by the upper atmosphere. The energy goes into heating the gas. Hydrogen, the lightest element, picks up the heat first. As the upper layers warm, hydrogen atoms reach speeds higher than the planet's escape velocity, and they leak away into space. This process is the same one that has been slowly stripping water from Venus for billions of years. On Proxima B, the rate is far higher, because the high-energy radiation flux is far higher. The second channel is what scientists call hydrodynamic escape. When the upper atmosphere gets heated enough, it does not just lose individual atoms, it expands. The whole upper layer puffs outward, reaching altitudes where the planet's gravity barely holds it. Once that puffed layer is moving outward as a coherent flow, heavier atoms get carried along by the lighter ones. Hydrogen drags oxygen, oxygen drags nitrogen. Whole atmospheric components leave as a single rising column. The third channel is direct stripping by the stellar wind. Charged particles in the wind plough into the upper atmosphere and physically knock atoms out. This is the process MAVEN documented at Mars. On Proxima B, with the wind density factor and the absent magnetic field factor multiplied together, the rate is potentially millions of times higher than at Mars. The fourth channel kicks in during flares and coronal mass ejections. Each flare delivers a pulse of high-energy radiation that briefly inflates the atmosphere. The atmosphere, suddenly puffed up, encounters the wind at higher altitude, where the wind has even more leverage. A larger fraction of the inflated layer gets ripped away in a single event. Then the planet has to wait until the next flare and lose more. The cumulative integrated effect over the lifetime of Proxima B is staggering. Calculations suggest the planet has received between 7 and 16 times the total high-energy ultraviolet and X-ray dose that Earth has received over the same span. Earth has lost meaningful amounts of hydrogen over 4.5 billion years under the gentle output of our home star. Proxima B has been losing atmosphere under conditions an order of magnitude harsher. The realistic outcome depends entirely on initial conditions we cannot measure. If Proxima B started with a thin atmosphere, that atmosphere is gone. If it started with a thick atmosphere, what remains today might be a remnant, perhaps 10 to 20% of the original mass, perhaps less. If the planet started with the gas budget of a small ice giant, even after billions of years of stripping, it might still hold a substantial atmosphere. The mission planners have placed their bets on the third option, mostly because the first two leave nothing to image. The extremely large telescope, scheduled to come online in 2028, will tell us which scenario is correct. The next waypoint is what the stripping does to water itself. Water is 2 hydrogen atoms bonded to 1 oxygen atom. The molecule itself is stable on Earth's surface and across most of the atmosphere. Up high in the rarefied layers above 90 kilometers, the picture changes. Ultraviolet light has enough energy to break the bonds. The molecule splits. The hydrogen atoms come free. The oxygen atoms come free. On Earth, a small fraction of water vapor reaches that altitude. A small fraction of that gets photolyzed. A small fraction of the freed hydrogen escapes the planet. The result is a slow, steady loss of water from Earth, slow enough that our oceans have remained almost intact for 4 billion years. The cold trap at Earth's tropopause helps. Water vapor freezes out before it can reach the dangerous high altitudes, returning as rain. Proxima B does not have Earth's cold trap. The radiation environment is too aggressive. The atmosphere, if it exists, is being heated and stirred constantly by stellar input. Water vapor, once injected into the atmosphere, has a far better chance of reaching the photolysis altitude where it gets ripped apart. Once water gets ripped apart, the hydrogen does what hydrogen always does. It heats up, it moves fast, it escapes the planet's gravity. Hydrogen is so light that even modest energy inputs send it past escape velocity, and the high-energy radiation environment on Proxima B provides far more than modest input. The oxygen left behind sits in the upper atmosphere. Some of it gets carried away by the same hydrodynamic flow that took the hydrogen. Hydrogen, escaping, drags oxygen with it through simple collisional coupling. Light gases pulling on heavy gases. The oxygen does not move as fast as the hydrogen on its own, but with hydrogen pulling, oxygen gets dragged out of the planet's gravity well. The net result is a process that converts liquid water on the surface into hydrogen and oxygen in the upper atmosphere, then exports both to interstellar space. Every gallon of ocean that evaporates and reaches high altitude becomes a gallon of atmospheric loss. Over geological time, the oceans drain into vacuum. There is a wrinkle that has caught the attention of researchers. If the hydrogen escapes faster than the oxygen, the planet ends up with a surplus of oxygen in its atmosphere. The oxygen, by itself, is one of the strongest biosignatures astronomers look for when imaging exoplanets. On Earth, free oxygen exists almost entirely because of photosynthesis. If we detect oxygen in a planet's atmosphere, it has historically been considered strong evidence that life is producing it. Proxima B breaks that assumption. A dry, dead, ultraviolet baked planet that lost its oceans to stellar wind and photolysis would still have an oxygen-rich atmosphere as a leftover signature of the loss process. Astronomers calling this an abiotic oxygen scenario have warned that when the extremely large telescope finally images Proxima B, finding oxygen would not necessarily mean finding life. It might mean finding the chemical fingerprint of a planet that used to have oceans. This is the sting in the data. The same processes that destroy habitability also produce false positives for habitability. A truly dead planet around Proxima Centauri might look chemically identical to a living one until much more detailed analysis is possible. The next waypoint examines what happens to whatever atmosphere survives the day side. Specifically, what happens when it reaches the night side. Whatever air Proxima B still has does not stay in one place. Atmospheric circulation moves gas across the planet, driven by the temperature gradient between the burning day side and the freezing night side. Hot air rises over the substellar point, flows outward toward the terminator and beyond, sinks over the night side, and returns along the surface in a return flow. This circulation pattern is the only thing keeping the night side from becoming a complete chemical graveyard. As long as warm air keeps arriving from the day side, the night side cannot fully cool. Heat gets continuously deposited. Gases stay gaseous. The atmosphere stays distributed. But the temperatures on the night side are extreme. Without any direct stellar input, and with the planet radiating heat outward into space, the dark hemisphere can fall well below the freezing point of water, well below the freezing point of carbon dioxide, and approaching the freezing point of nitrogen itself. Atmospheric models suggest surface temperatures on the night side might dip below -160 Celsius, cold enough to freeze almost any gas that drifts across. Once a gas freezes onto the surface, it stops circulating. It becomes ice. The ice sits there in permanent darkness, accumulating, while more gas drifts over from the day side and joins it. Over time, the night side acts as a one-way drain on the atmosphere. Gas flows in. Ice accumulates. The total amount of gaseous atmosphere decreases. Climate modelers call this a cold trap, and on Proxima B, it is potentially catastrophic. If the atmosphere is too thin to maintain efficient heat transport, the cold trap wins. Gases freeze faster than they can be returned to the day side. The atmosphere collapses entirely onto the night side as a thick layer of frozen carbon dioxide and water ice. The day side becomes a vacuum-exposed rock face, and the night side becomes an ice cap in permanent shadow. The trigger condition for collapse is a thin enough atmosphere that the day-night winds cannot keep up with the freezing rate. Estimates from teams running general circulation models suggest the cutoff is somewhere around half an Earth atmosphere of total surface pressure, depending on composition. Below that threshold, collapse becomes likely. Above it, the winds win and the atmosphere stays distributed, although night-side ice deposits still build up at lower rates. There is something macabre about how this scenario evolves. Suppose Proxima B started with a thick atmosphere, lost the bulk of it to stellar stripping over billions of years, and is now sitting just above the collapse threshold. Each additional flare event, each subsequent stripping event, brings the planet closer to the cliff edge. At some point, the threshold gets crossed. The remaining gas freezes onto the night side faster than it can return. The winds slow. The freezing accelerates. Within years to decades, the entire residual atmosphere migrates to the dark hemisphere as ice. The day side becomes airless rock. If we arrive too late with our probe, we image a world that already collapsed. The day side has black sky and direct sunlight on bare regolith. The night side has buried itself under a frozen white shell of what used to be air. If we arrive earlier in this evolutionary track, we might catch a planet still hanging on, still circulating, still potentially holding a thin atmosphere together by the winds. Alone. The next waypoint puts a number on the youth problem that drove all of this loss. Proxima Centauri is older than our home star. The best estimates from stellar evolution models place its age somewhere between 4.8 and 7 billion years, compared to our home star's 4.6 billion. That extra age matters, because red dwarfs do something specific in their early years that larger stars do not. For roughly the first billion years of a red dwarf's life, the star is far brighter and far more active than it will be later. This is sometimes called the saturated phase. During this period, the star outputs high-energy ultraviolet and X-ray radiation at intensities up to 100 times the levels it will produce in middle age. The flare rate is higher. The wind is denser. The whole environment around the star is far more hostile during the first billion years than during the next 10. A planet born in the warm zone of a red dwarf does not get a quiet childhood. It gets a billion-year ultraviolet bombardment far worse than anything its star will throw at it later. The cumulative numbers are punishing. Proxima B, integrated over its full history, has received between 7 and 16 times the total high-energy ultraviolet and X-ray dose that Earth has received over the same span. Most of that dose was delivered during the first billion years, before the star calmed into its current behaviour. By the time the star quieted to its present level, the damage was already done. Earth's atmosphere has been losing hydrogen for 4.5 billion years under our home star's relatively gentle output, and Earth still has its oceans because the loss rate has been low. Proxima B has been losing hydrogen and other light gases under a flux up to 16 times higher, integrated over its lifetime. Whatever the planet started with, the youth phase took most of it. This is why even optimistic atmospheric models for Proxima B include a major caveat. The planet might have had a thick primary atmosphere when it formed, dominated by hydrogen and helium captured from the protoplanetary disk. That primary atmosphere is gone. It evaporated during the saturated phase of the star. What remains, if anything, is a secondary atmosphere. Gases outgassed from the planet's interior over geological time, from volcanism and from impacts. The secondary atmosphere is also at risk. The same processes that stripped the primary atmosphere are still active, just at lower rates. Whatever the volcanism rate of Proxima B, it has had to continuously replace gas faster than the star strips it away, for billions of years, just to maintain any atmosphere at all. There is a particular signature that researchers look for related to this youth problem. The ratio of deuterium to hydrogen in any remaining water tells us how much of the original hydrogen has escaped. Deuterium, the heavier isotope of hydrogen, escapes more slowly than ordinary hydrogen. A planet that has lost most of its water to stellar stripping ends up with a deuterium to hydrogen ratio far higher than its original value. Venus shows this signature dramatically, with around 150 times Earth's ratio, evidence of catastrophic ancient water loss. If the extremely large telescope can measure this ratio in Proxima B's atmosphere, assuming there is still an atmosphere to measure, the value will tell us how much water the planet has lost since formation. The expected number, based on the youth phase models, is high. The next waypoint examines a threat the youth phase pioneered, which the present-day star still produces regularly. The mass ejections. A coronal mass ejection is a flare's bigger, slower cousin. While a flare delivers radiation in seconds, a coronal mass ejection delivers physical material in hours or days. A chunk of the star's outer atmosphere, 1 billion tons of charged plasma, threaded with magnetic field, gets blown off the surface and hurled into space at speeds of millions of miles per hour. If that plasma cloud hits a planet, the impact is not a burst of light. It is a physical collision with stellar material. Our home star produces coronal mass ejections regularly, but most of them miss Earth. The geometry has to be right. The eruption has to point in our direction. Even when one does hit, Earth's magnetic field channels most of the particles to the polar regions, where they produce auroras and minor radio interference. Earth has been hit by several thousand of these events since humans started watching, and the cumulative atmospheric loss from them is small. Proxima B cannot dodge. The planet sits 4.5 million miles from its star. The angular size of the planet, from the star's perspective, is much larger than Earth's angular size from our star's perspective. Mass ejections leaving Proxima Centauri have a substantially higher chance of hitting Proxima B than equivalent ejections from our home star have of hitting Earth. The geometry alone increases the impact rate by orders of magnitude. The energy and density of the impacts are also worse. Coronal mass ejections from active red dwarfs, modelled by the team at NASA Goddard, can carry plasma densities at Proxima B's orbit that are hundreds of times higher than what Earth experiences from our home star's events. The dynamic pressure of an arriving cloud can briefly exceed the planet's atmospheric pressure at the upper altitudes, ripping away meaningful chunks of air in a single event. The frequency is the worst part. Proxima Centauri produces flares and likely coronal mass ejections at a rate of approximately one significant event per day, with superflare-class events every 5 years or so. A planet getting hit every day is a planet that never gets to recover. Each event chips off another piece of atmosphere. Each event briefly opens the atmosphere to deeper radiation penetration. Each event resets whatever chemical equilibrium the atmosphere had managed to reach. There is a specific scenario that planetary scientists worry about. If Proxima B has any residual magnetic field, that field gets hammered by each coronal mass ejection. The field lines compress against the planet on the day side. Reconnection events between the star's magnetic field and the planet's magnetic field dump energy directly into the upper atmosphere. The atmosphere puffs outward, exposes more material to the wind, and loses more mass. The cycle repeats with the next event. What this means for the mission profile is that Proxima B's atmosphere, if it exists, is a thin and dynamic layer being continuously eroded by physical collisions with stellar material. It is not a stable equilibrium. It is a transient state, maintained only as long as the planet's interior outgasses fast enough to replace what the star steals. The probe arriving in 25 years from launch will image a snapshot of this dynamic. Whatever gas signature we see will represent that single moment, the most recent steady state between the planet's outgassing rate and the star's stripping rate. The next waypoint asks why the star is so violent in the first place, and the answer comes from inside it. Stars come in many sizes, and the size of a star determines almost everything about how it behaves. Big stars burn fast and die young. Medium stars like our home star burn for 10 billion years and develop layered interiors. Small stars, the red dwarfs, burn for hundreds of billions of years. But they pay for that longevity with internal violence that lasts the whole time. Proxima Centauri has about 1/8 the mass of our home star. At that mass, the star's interior cannot sustain the layered structure that bigger stars use to keep their magnetic activity controlled. Inside our home star, energy generated at the core travels outward through a quiet radiative zone for about 70% of the radius, where photons slowly bounce their way up. Above that radiative zone, a convective zone takes over, with hot plasma physically rising and cooler plasma sinking. The radiative zone acts as a buffer, keeping the chaotic motions of the convective zone away from the core. Proxima Centauri has no radiative zone. The entire interior is one big convective system, all the way from the surface down to the fusion core. Hot plasma from the core rises directly to the surface. Cool plasma from the surface sinks directly to the core. The whole star is a single boiling cauldron, with no quiet middle layer to dampen the flow. This fully convective architecture has a specific consequence for magnetic fields. The magnetic field of a star is generated by the motion of conductive plasma, the same dynamo principle that generates a planet's field. In a layered star like ours, the dynamo operates mostly at the boundary between the radiative zone and the convective zone, in a thin shear layer called the tachocline. The boundary provides a stable surface for the field to organise against. In a fully convective star, there is no tachocline. The dynamo has nowhere stable to anchor. Instead, the magnetic field gets generated everywhere at once, in chaotic patches across the whole stellar interior, twisting and tangling as the convection moves them around. The field never settles into a clean dipolar geometry. It exists as a tangled mess of small-scale loops and bundles all over the star, constantly stretching and snapping. Every snap is a flare, every reorganization is an eruption. Every reconnection event releases stored magnetic energy. Because the chaos is happening everywhere, all the time, the flare rate is high, the flares come from every latitude, and the star never has a quiet period. This is the engine that drives everything bad about Proxima Centauri. The fully convective structure is not a temporary phase. It is the star's permanent architecture, and it stays this way for as long as the star burns hydrogen, which, for a star this small, is hundreds of billions of years. Trillions, by some estimates. A planet around a fully convective red dwarf is not facing a phase that will end. It is facing a steady state that will outlast the universe's current age many times over. There is no future calm period to wait for. There is no settling down period. The star is doing now exactly what it was doing 4 billion years ago, and exactly what it will be doing 4 trillion years from now. This permanence is part of why the data on Proxima B's habitability has been so consistently grim. The star is not having a bad century. The star will be having a bad eternity. The next waypoint examines a specific data set that revealed how violent this star really is, because for a while, astronomers thought they had found a planetary system around it. In late 2017, a team led by Guillaume Anglada, the same family name as the discoverer of Proxima B, but a different astronomer, published a paper that excited everyone in the exoplanet community. Using observations from the Atacama Large Millimeter Array, the ALMA telescope in Chile, they reported the detection of dust rings around Proxima Centauri. This was big news. Dust rings around stars are diagnostic. Earth's solar system has them, in the form of the asteroid belt and the Kuiper belt, both of which are leftover debris from planet formation. Where you see dust rings, you usually have planets, because the rings are sculpted by gravitational interactions with larger bodies. The reported rings around Proxima Centauri suggested that the system was not just Proxima B alone. It was a full planetary system, with rocks and ice and possibly more planets, arrayed in concentric rings the way Earth's solar system arrays its own debris. For a few months, mission planners worked with this picture. A planetary system implied targets beyond Proxima B. It implied a richer environment for any future probe. It implied, frankly, that the system was more like home than we had thought. Then a different team, led by Meredith McGregor at the Carnegie Institution and Alicia Weinberger, reanalyzed the same ALMA data set. Instead of averaging the data over the full observation period, they looked at how the brightness changed minute by minute. What they found killed the dust ring story. On March 24, 2017, during one of the ALMA observation runs, Proxima Centauri produced a flare, a big one. The flare lasted less than 2 minutes out of the 10 hours ALMA observed the star. During that brief window, the star's millimeter wave brightness jumped by a factor of around 1,000. When the original team averaged their entire observation period together, that 2-minute superflare blended into the baseline. The averaged signal looked like a small, persistent excess of millimeter wave light. A small, persistent excess of millimeter wave light is exactly what a dust ring would look like. The two signals were indistinguishable in the average data. The original team interpreted the excess as cold dust re-radiating starlight at long wavelengths. The McGregor reanalysis showed the excess was actually a transient flare that happened during a short window of the observation. When the flare was subtracted, the dust ring disappeared. The remaining baseline was consistent with no dust at all, or with dust at quantities far below what the original analysis claimed. The implication for Proxima B's habitability is direct. The dust ring story suggested a relatively gentle stellar environment with a normal planetary system structure. The flare-only story confirmed something far worse. Proxima Centauri's flares are so bright at millimeter wavelengths that a single event, lasting under 2 minutes, dominated 10 full hours of ALMA observations. Any star that can do that to a precision radio telescope is a star that is doing something equally aggressive to any planet sitting nearby. The flare also gave researchers their first millimeter wave characterization of a Proxima Centauri superflare, separate from the optical everyscope data. The two events confirmed each other. The star is not occasionally violent, it is regularly violent across multiple wavelength bands with energy budgets that dwarf anything our home star produces. The dust ring became a casualty of measurement. The flare was the real signal. The next waypoint examines why we cannot directly watch this planet, and what that limitation forces our missions to do. The single most powerful tool astronomers have for studying exoplanet atmospheres is the transit. When a planet passes directly between its star and Earth, a small fraction of the starlight has to pass through the planet's atmosphere on its way to us. That filtered starlight carries chemical fingerprints. Different gases absorb different wavelengths. By comparing the spectrum of the star during a transit to the spectrum during a non-transit, astronomers can extract a list of molecules in the planet's atmosphere with remarkable precision. This is how the James Webb Space Telescope has characterized the atmospheres of dozens of distant worlds. It is how we know certain hot Jupiters have water vapor. It is how we know specific super-Earths have either thick atmospheres or none at all. Transits are the workhorse of modern exoplanet atmospheric science. Proxima B does not transit. Or at least, no transit has ever been detected, despite extensive searches. The geometry is the problem. For a planet to transit its star, the orbital plane has to align almost perfectly with our line of sight. Even a small tilt in the orbit, just a few degrees off from edge-on, means the planet passes above or below the star from our perspective. We see no dimming. The transit method gives us nothing. For Proxima B, surveys have ruled out any detectable transits. The microvariability and oscillations of STAR's satellite watched the star for 38 days and saw no transits. The Bright Target Explorer mission watched for additional intervals. Ground-based campaigns have repeatedly tried. Nothing. The probability of Proxima B transiting from our perspective was estimated at roughly 1 to 2% based on the orbital geometry, and that probability has now collapsed to essentially 0 based on the failed searches. What this means for habitability research is that one of the best tools available is unavailable. We cannot use transit spectroscopy on Proxima B. We cannot watch starlight filter through its atmosphere. We cannot pull out the chemical fingerprints that would tell us whether the planet has water vapor, oxygen, methane, or any other gas. Every other exoplanet of comparable interest, the ones we read about with biosignature detection claims, has a transit. The TRAPPIST-1 planets transit. K2-18b transits. Most of the famous habitable zone candidates transit. Proxima B is the closest one and the only one we cannot study this way. The mission planners have had to design around this limitation from the start. To learn anything about Proxima B's atmosphere, the alternatives are direct imaging, physically resolving the planet as a separate dot of light next to the star, or sending a probe. Both options are extraordinarily hard. Direct imaging requires telescopes that can suppress the glare of the star by factors of billions, and even then, the planet appears as a single pixel. The extremely large telescope being built in Chile, scheduled to come online in 2028, will be the first instrument theoretically capable of imaging Proxima B. Directly. Its primary mirror is around 40 meters across. It will use sophisticated coronagraphs to block the star's light. It might, with luck, get a single pixel detection of the planet. Spectroscopy on that single pixel would yield limited atmospheric data, far less than a transit would provide. The probe option is the topic of the next several waypoints. a spacecraft physically going to the planet would dwarf any remote observation in detail. The cost is the time required and the engineering challenges of getting there. The next waypoint sets the stage by examining what direct imaging from the ELT might actually tell us. The extremely large telescope being built atop Cerro Armazones in northern Chile is the largest optical telescope humanity has ever attempted. Its primary mirror is 39 meters across, made of 798 hexagonal segments fitted together with sub-millimeter precision. The light-gathering area is roughly 200 times that of the Hubble Space Telescope. When it sees first light, currently scheduled for the end of 2028, it will outperform every existing optical instrument by a wide margin. The ELT was designed with several specific science targets in mind. One of them is Proxima B. The telescope's combination of huge collecting area, advanced adaptive optics, and a sophisticated coronagraph called Harmony gives it a theoretical chance of separating the planet's light from the stars, despite the angular separation being only about 37 thousandths of an arcsecond, roughly the angular width of a coin held at the distance of 50 miles. If the ELT succeeds in resolving Proxima B, the data product is a single point of light. That point contains the entire planet, blurred into one pixel. There is no surface map, there is no continent detection. There is one bright spot distinct from the star with a measurable spectrum. That spectrum is the prize. Different wavelengths of the planet's light correspond to different processes. Reflected starlight in the visible band tells us the planet's albedo, how shiny or dark it is. Sharp absorption features in the red and infrared tell us which gases sit in the atmosphere, if any. Polarization signatures tell us whether there is liquid water on the surface, because liquid water reflects polarized light differently than rock or ice. The spectroscopic targets the ELT team has prioritized are oxygen, water vapor, methane, and carbon dioxide. Oxygen would be the historical biosignature, although the previous waypoint on hydrogen drag established that abiotic oxygen is a real possibility on planets that have lost their oceans. Water vapor would suggest some surface liquid water remains. Methane, especially if found alongside oxygen in a chemically unstable combination, would be one of the strongest possible indicators of active biology. Carbon dioxide tells us about the atmospheric structure and the planet's greenhouse state. The complication is that the ELT cannot do real transit quality spectroscopy. Without a transit, the absorption features are weaker, the signal to noise is harder to extract, and the measurements take many hours of observation time. Some atmospheric gases are detectable, others, particularly trace species, are likely beyond reach. There is also a fundamental ambiguity built into any direct observation. The ELT measures light reflected from the planet's day side. If Proxima B's atmosphere has been collapsed onto the night side, the day side might look spectroscopically dead, bare rock, no atmospheric absorption, no water signature. That result is consistent with two scenarios. Either the planet never had an atmosphere, or it had one and lost it. The ELT alone cannot distinguish these cases. If the spectrum shows atmospheric features, those features confirm that Proxima B retains some gas envelope. The composition tells us which scenarios from earlier waypoints are correct. A nitrogen-oxygen atmosphere would suggest Earth-like. A carbon dioxide atmosphere would suggest Venus-like. A hydrogen-helium atmosphere would suggest a leftover primordial envelope, which would be a major surprise. Whatever the ELT finds, it will be the first real chemical data on the closest potentially habitable world. Until 2028, every habitability discussion about Proxima B is informed speculation. After 2028, some questions get hard answers. The next waypoint imagines what a habitable Proxima B would actually look like. Strip away the worst-case scenarios for a moment. Imagine the ELT spectroscopy in 2028 reports water vapor, suggests an atmosphere thick enough to maintain circulation, and shows polarization signatures consistent. With liquid water on the surface, what would Proxima B actually look like? The picture starts with the day side. Standing under the substellar point, you would see Proxima Centauri filling part of the sky. The disk would be roughly 3 times the angular diameter that our home star shows from Earth, because Proxima B is so much closer to its star. The light is deep red, not white. The wavelengths peak in the near-infrared. To human eyes, the sky would feel like permanent twilight, with everything bathed in a warm reddish glow. The water under your feet, if there is water, sits as an ocean. Climate models suggest the dayside ocean of a habitable Proxima B would be permanently warm, possibly tropical, with temperatures around 20 to 30 Celsius at the substellar point. The ocean would be calm in the centre, where convection drives air upward and surface winds are minimal. Around the edges of the ocean, where the dayside meets the terminator, the winds pick up. Walking outward from the substellar point, in any direction, you eventually reach the terminator. The star, which had been overhead, slides lower in the sky. There is no sunset. The star simply settles to a permanent position above the horizon and stays there. Below your feet, the warm ocean transitions to cooler water, then to ice. The terminator is a ring of melting glaciers where the warm ocean from the dayside runs into the frozen wastes of the nightside. This terminator zone is where every climate model places the most interesting weather. Permanent storm fronts hover here. The temperature gradient drives violent winds, possibly exceeding 200 miles per hour as a baseline. Rainfall patterns, if rain falls, would be locked in place by the geography. A mountain range running across the terminator would have a wet face on the dayside and a dry face on the nightside for the entire history of the planet. Crossing the terminator, you enter the nightside. The star drops below the horizon and stays there. The temperature plummets. The ocean, if it extends this far, has frozen into a thick ice shell. The ice gets thicker as you move further toward the antistellar point, the spot directly opposite the substellar point, where the night is deepest. There is one possibility for liquid water on the night side, even in a habitable scenario. Heat from the day side, transported by the circulating ocean and atmosphere, could keep a layer of liquid water under the night side ice. This is exactly the situation on Earth's moon Europa, where a frozen surface caps a deep liquid ocean. On Proxima B, an under-ice ocean might extend across the entire night side, fed by warm currents from the day side, isolated from the ultraviolet bombardment of the surface. If life exists on Proxima B, the under-ice ocean might be its safest home. Shielded from radiation by yards of ice, fed by chemical and thermal energy from the planet's interior, it would resemble the deep biospheres of Earth's hydrothermal vents. The probe arriving from Earth could not see this ocean directly, it would only image the surface. But if Proxima B is alive, the life is most likely down there, beneath the ice cap of a world that turned half its face permanently away from its star. The next waypoint examines the scientific name for this geometry. When climate modelers run general circulation simulations for tidally locked planets in the warm zones of red dwarfs, the same picture keeps emerging. They call it the eyeball model, and the term is descriptive enough that it needs little explanation. Looking down at the planet from above, you see concentric circles. The centre is hot, the edges are cold, the boundary between them is sharp. The whole world looks like a giant eye, with a warm pupil at the substellar point and frozen white sclera covering the rest. The terminator forms an iris of habitable transition zone between the two extremes. The eyeball geometry has been simulated in dozens of independent papers using different climate codes. Teams at NASA Goddard, the Met Office in the United Kingdom, the University of Chicago, and the Max Planck Institute have all run versions of this model with different atmospheric compositions, different planetary masses, and different rotation states. The results converge. Tidal locking plus moderate greenhouse atmosphere plus warm zone orbit equals an eyeball. The simulations agree on the essential structure, but disagree on the details. The size of the warm pupil depends on how thick the atmosphere is and how much heat the winds can transport. A thin atmosphere produces a small, intensely hot pupil, and a large, deeply frozen wasteland. A thick atmosphere produces a wider, milder pupil and a less extreme cold side. Past a certain atmospheric thickness, the temperature gradient evens out enough that the eyeball pattern fades into something closer to a uniformly warm planet. That uniformly warm scenario requires a lot of greenhouse gas. Estimates suggest several Earth atmospheres of carbon dioxide would be needed to redistribute heat efficiently enough to prevent night-side freezing. Whether Proxima B has that much carbon dioxide remains open. The youth phase atmospheric stripping likely removed any thick primordial envelope. What remains would have to come from outgassing over the planet's history, and depends on the planet's interior heat budget and tectonic activity. There is a more subtle feature in the simulations that gets less attention. The substellar point is not just hot, it is a permanent rising air mass. Hot air moves upward, fueling the formation of clouds directly above the substellar region. Climate models predict a thick, persistent cloud deck right over the warmest spot on the planet, reflecting a substantial fraction of the incoming starlight back to space before it reaches the surface. This cloud deck is a kind of natural thermostat. As the substellar point heats up, more clouds form, more starlight gets reflected, the temperature stabilizes. The thermostat extends the range of conditions under which Proxima B might remain habitable by automatically pushing back against runaway heating. The simulations also predict consistent atmospheric circulation patterns. Air rises over the substellar point, flows outward in the upper atmosphere toward the night side, sinks over the antistellar point, and returns along the surface. The return flow at the surface drives the strong terminator winds that keep the cold trap from collapsing. The whole system is dynamic. Heat moves, air circulates. Water might evaporate from the dayside ocean, get carried by upper atmosphere winds toward the night side, snow out as ice over the terminator, and slowly melt back toward thee. Dayside as the ice flows downhill under gravity. A complete planetary water cycle, geometrically frozen in shape but chemically active. The eyeball model is the best-case habitability scenario for Proxima B. It is the picture mission planners hope to confirm. The next waypoint examines the picture they fear instead. Venus is the cautionary tale, same size as Earth, similar mass, formed from the same material, and yet Venus has a surface hot enough to melt lead, an atmosphere thick enough to crush a submarine, and clouds, made of sulfuric acid. The reason is simple. Venus orbits closer to its star than Earth does. The extra heat triggered a runaway process billions of years ago, and Venus has been baking ever since. The runaway greenhouse works through a feedback loop. Higher temperatures put more water vapor into the atmosphere. Water vapor is itself a powerful greenhouse gas. More water vapor means higher temperatures. The cycle accelerates. Eventually, all the water boils off the surface entirely, gets carried into the upper atmosphere, and gets photolyzed by ultraviolet light. The hydrogen escapes to space. The oxygen reacts with surface rocks. The water is gone forever. This process is irreversible. Once a planet enters the runaway state and loses its water, it cannot recover. The surface heats further because there is no longer any liquid water to absorb heat through evaporation. Surface rocks bake. Volcanic activity releases additional carbon dioxide, which has nowhere to go because there are no oceans to dissolve it and no weathering cycle to remove it. The atmosphere thickens. Temperatures climb. Venus today, 4.5 billion years after its presumed runaway, sits at a surface temperature of around 460 Celsius, hot enough to glow in the dark. Proxima B sits in a very different stellar environment than Venus, but the runaway risk is real. The planet receives about 65% of the starlight Earth receives, but with a different spectrum, heavier in the near-infrared, lighter in the visible. The infrared bias matters because near-infrared light gets absorbed by water vapor far more efficiently than visible light. A planet receiving infrared heavy radiation is a planet primed for a runaway, because the same incoming flux drives more atmospheric heating than the equivalent flux from a sun, like star would. Climate models accounting for this spectral effect have produced mixed results. Some simulations show Proxima B safely outside the runaway zone, with stable surface temperatures and persistent oceans. Others show the planet right at the edge, where small variations in atmospheric composition determine whether the planet stabilizes or runs away. A few simulations show outright runaway, with the model boiling off all surface water within geological time and producing a Venus analogue. The youth phase of the star matters for this question. During the first billion years, Proxima Centauri was substantially more luminous than today. Even a planet currently outside the runaway zone might have crossed the runaway threshold during the saturated phase of its star, lost its water, and stayed dry afterward. By this scenario, the present-day Proxima B is a desiccated world that sits within the formal habitable zone, but is actually as dry as Venus, simply because it baked early and never got its water back. There is no easy way to distinguish between a habitable Proxima B and a runaway Proxima B from Earth-based observations. Both might show carbon dioxide signatures. Both might show similar temperatures. The differentiating signature is the presence or absence of liquid surface water, which is detectable through polarization measurements, but only with very high signal-to-noise, likely beyond what the ELT can achieve in reasonable observing time. The runaway scenario is one of the two main bad outcomes. The other is the opposite extreme. The next waypoint examines what happens if Proxima B is a snowball. If Proxima B lost too much of its greenhouse atmosphere during the youth phase of its star, the result is not a runaway. The result is the opposite. A planet without enough greenhouse gas to retain heat radiates its energy back into space and cools dramatically. Surface water freezes. Ice spreads. The planet locks into a permanent cold state. This is the snowball scenario, and Earth experienced it at least twice during the Cryogenian period, around 600 to 700 million years ago. During those events, ice covered most of Earth's surface, including the equator. Earth eventually escaped through volcanic carbon dioxide buildup and a slow greenhouse recovery. Proxima B might not have that escape route. The snowball state is stable in a particular way. Ice has a much higher albedo than rock or water. Ice reflects something like 70% of incoming starlight back to space. Once a planet's surface is mostly ice, it absorbs less starlight, which keeps it cold, which keeps the ice from melting. The system locks itself into a frozen configuration. For Earth, escaping the snowball required a slow build-up of volcanic carbon dioxide over millions of years, eventually producing enough greenhouse warming to overcome the high albedo and start melting the ice. Once melting began, the feedback reversed. Less ice meant more absorbed starlight, meant warmer temperatures, meant more melting. Proxima B has different physics. Because it is tidally locked, the substellar point always receives direct radiation. Even a snowball Proxima B would have a hotspot. Climate modelers have nicknamed this scenario the eyeball with frozen sclera, where the dayside substellar region remains warm enough to keep a small circle of liquid water, while the rest of the planet stays frozen. This configuration might be the most likely outcome if Proxima B currently has a thin atmosphere. The substellar ocean would be a small disk of liquid water surrounded by ice on all sides, with no terminator strip of habitability and no night side under ice ocean. The whole planet, except for one circular pool, is frozen. There is a curious feature of this scenario. The substellar pool would be deep, because it represents the only place where geothermal heat from the planet's interior can reach the surface without freezing on contact with. The atmosphere. The ice everywhere else acts as an insulator, trapping interior heat below. At the substellar point, where surface heating overcomes interior cooling, a hole appears in the ice and exposes liquid water to direct stellar exposure. That liquid water is what the ELT might detect. Polarization measurements aimed at Proxima B's dayside, if they show evidence of liquid water reflection, do not necessarily mean the planet has Earth-like oceans. They could mean the planet has a single substellar pool surrounded by frozen wasteland. The substellar pool, if it exists, would be intensely interesting from an astrobiology standpoint. The temperature, the chemistry, the stable geometry, the constant illumination, all of these create conditions different from anywhere on Earth. Whatever might live in that pool would be adapted to a permanently illuminated, geometrically constrained habitat that has remained essentially unchanged for billions of years. But the radiation problem returns with force. The substellar pool is the place on the planet most exposed to flares. The water has to be deep to provide radiation shielding. The surface layers would be sterilized regularly by superflares. Anything alive would have to live in the depths, away from the constant ultraviolet bath. The next waypoint examines what happens when humans try to listen for any signal from this place. In 2019, the Breakthrough Listen project, which uses the Parkes Observatory in Australia and the Green Bank Telescope in West Virginia to search for radio. Signals of Artificial Origin was monitoring Proxima Centauri as part of its survey of nearby stars. The project records vast quantities of radio data and processes them with algorithms designed to flag anything that looks technological. Narrow band signals, modulated patterns, anything that doesn't match natural astrophysical emission. In April and May of 2019, during routine observation, the system flagged something, a narrow band signal at 982 MHz, appearing in the data when the telescope was pointed at Proxima Centauri, disappearing when the telescope was pointed. Elsewhere, the signal had the spectral characteristics of an artificial transmission. It became known as BLC-1 for Breakthrough Listen Candidate 1. For about a year, the BLC-1 signal sat in the project's database, not announced publicly, while the team did the careful work of trying to rule out alternative explanations. The signal had the worrying property that signals from genuine extraterrestrial sources would not. It appeared at exactly the wavelength predicted for some forms of low-power radio communication, suggesting a deliberately engineered transmission. The frequency drift, which would normally betray a Doppler shift from a moving source, was minimal, consistent with a stationary source rather than a planet orbiting a star. By late 2020, the news had leaked, and the team published their analysis in 2021. The verdict was disappointing. BLC-1 was almost certainly terrestrial interference, not a signal from Proxima Centauri. The frequency, the modulation, the appearance pattern all matched a class of human-generated radio noise that occasionally drifts into wavelength bands used for radio astronomy. The signal was real. Its source was Earth. The BLC-1 episode taught the search community something useful about the difficulty of confirming any positive detection. Even with all the safeguards, a single survey produced a candidate that took a year of careful investigation to rule out. The signal-to-noise problem in interstellar communication searches is severe, and the false positive rate is real. The episode also highlighted what we would actually expect from Proxima B if life were present and broadcasting. The planet sits 4.2 light-years away. Any signal we detect today was sent 4.2 years ago. Round-trip communication, even at the speed of light, would require 8.4 years for a single back and forth. Real-time conversation is impossible. More fundamentally, life on Proxima B would face every habitability challenge previously discussed. Surface life is unlikely given the radiation environment. Under ice life, if it exists, has no obvious reason to develop technology, since it has no exposure to the surface, no view of the stars, and no astronomy to motivate. Communication. The radiation that strips Proxima's atmosphere and threatens any surface biology also blocks the most natural pathways by which a civilization might emerge. If Proxima B harbours life, that life is almost certainly microbial, almost certainly subsurface, and almost certainly silent. The radio searches will continue because they cost relatively little to run, but the expectation among the searchers is that Proxima Centauri will remain quiet. The silence in itself is not evidence of nothing. It is evidence of one specific thing, that we have not yet detected a deliberate signal. Many other forms of evidence remain accessible, primarily through direct observation and eventually through physical visitation. The next waypoint examines what physical visitation actually requires, starting with the time problem. Voyager 2 left Earth in 1977. It is currently in interstellar space, having crossed the heliopause in 2018. It is moving at around 34,000 miles per hour. By any measure, it is one of the fastest spacecraft humans have ever launched, and it is moving in roughly the right direction to encounter the Alpha Centauri system in the deep. Future. If Voyager 2 were aimed precisely at Proxima Centauri, which it is not, it would arrive in approximately 75,000 years. Take that number and let it settle. 75,000 years is roughly the entire span of human civilization multiplied by 10. It is longer than the time since Homo sapiens left Africa. It is longer than the existence of any continuous human institution. A spacecraft launched today, using the fastest sustainable propulsion humanity has ever deployed, would arrive at Proxima B after a journey roughly equivalent to all of recorded. History. This is the central problem of interstellar travel. The speed available with conventional propulsion is too low. The chemical rockets that put Voyager 2 on its trajectory burn for minutes, and then coast for the rest of the mission. The acceleration is high while the burn lasts. The total energy available is small. Once the propellant is gone, the spacecraft is locked at whatever speed the burn delivered. Faster propulsion has been studied extensively. Nuclear pulse propulsion, developed under Project Orion in the 1950s and 60s, would have used small nuclear explosions to push a spacecraft at sustained. Accelerations. The math works, in principle. A Project Orion vessel could reach Proxima Centauri in around 1,000 years. The political and environmental obstacles to detonating thousands of nuclear devices in space ended the program in the 60s, and no serious revival has been attempted. Nuclear thermal propulsion uses a nuclear reactor to heat propellant. It offers maybe twice the efficiency of chemical rockets. A nuclear thermal probe to Proxima Centauri would take tens of thousands of years instead of 75,000, an improvement, but not a meaningful one for human-scale missions. Fusion propulsion, if achieved, could potentially reach Proxima Centauri in a few hundred years. The catch is that we have not built a sustained fusion reactor on Earth, much less a compact one capable of operating in space. Fusion-powered interstellar travel remains a category of speculation rather than engineering. Antimatter propulsion offers the highest theoretical specific impulse of any concept ever proposed. A few grams of antimatter, fully annihilated, would deliver enough energy for a fast trip to Proxima Centauri. The problem is producing antimatter. Current production rates at facilities like CERN are measured in nanograms per year, at costs equivalent to many billions of dollars per gram. A practical antimatter mission would require manufacturing antimatter at industrial scales we do not know how to achieve. These are the slow options. Each one offers an improvement over Voyager 2. None of them gets a probe to Proxima B in less than centuries. Centuries-long missions raise their own problems: the durability of the spacecraft, the institutional continuity required to receive the data when it eventually arrives. The question of whether anyone in 700 years will care about results from a probe launched in our era. There is one fast option that has been worked out in detail. It does not use rockets at all. It uses light fired from Earth, hitting a sail on the spacecraft. That option is the next waypoint. In April 2016, 4 months before the announcement of Proxima B, an unrelated project called Breakthrough Starshot was announced at a press conference in New York. The project's funder was Yuri Milner, a Russian billionaire who had committed $100 million to feasibility research. The project's advisory board included Stephen Hawking, Mark Zuckerberg, and a roster of physicists and aerospace engineers. The goal was simple to state and almost impossible to engineer. Send a fleet of small probes to Alpha Centauri at 20% the speed of light, getting them there within 20 to 30 years of launch. The arrival of the planet announcement 4 months later gave Starshot a target. Proxima B became the most natural destination for the proposed probes. The mission profile was redrawn around it. The probes would fly past at 60,000 kilometers per second, image the planet during the brief flyby window, and beam the data back across 4 years of empty space to Earth. The Starshot architecture is unlike any spacecraft mission ever flown. The probes themselves are tiny. Each probe, called a starchip, is a centimetre-scale wafer carrying a camera, a power source, a navigation system, and a laser communicator. The total mass of each starchip is in the gram range. Several thousand of these chips would be carried into Earth orbit by a conventional rocket, then released into deep space. Each starchip is attached to a light sail. The sail is roughly 4 meters across, made from material thinner than 100 nanometers and weighing about a gram. The combined mass of chip plus sail is small enough that a sufficient burst of light pressure can accelerate it to substantial velocities. The light comes from Earth. The Starshot proposal calls for a phased array of ground-based lasers totaling around 100 gigawatts of power output focused onto a single sail at a time. The laser fires for approximately 10 minutes. During that 10-minute burn, the sail accelerates from orbital velocity to 20% the speed of light. The acceleration is roughly 10,000 times Earth's gravity. After 10 minutes, the laser shuts off, and the starship coasts for the next 20 years across interstellar space. 20 years is the optimistic estimate. The actual transit time depends on the achieved velocity, which depends on the laser power, the sail efficiency, and the starship mass. A more realistic estimate, given current technology, might be 25 to 30 years. Even at that pace, a starship launched in the 2030s could reach Proxima B before mid-century. The mission is not one probe, it is a swarm. The Starshot architecture assumes that most probes will fail. Some will be lost during the laser acceleration phase, when the sail might tear, the chip might overheat, or the alignment might fail. Some will be lost during the interstellar coast, when collisions with dust grains will be statistically certain. Some will simply miss the target. The expectation is that of 1,000 starships launched, perhaps a few dozen will arrive intact and oriented correctly to image Proxima B. A few dozen successful probes from a fleet of 1,000 is the success criterion. The mission tolerates a 97% failure rate because the cost per probe, after the laser array is built, is small. The expensive part is the laser. The probes themselves are mass-produced commodity items. Each component of this architecture has its own engineering crisis. The next waypoint starts with the laser itself and the acceleration it has to deliver. The Starshot laser has to do something no laser system in human history has come close to doing. It has to deliver 100 gigawatts of power, focused on a target 4 meters across, hold that focus while the target races away from Earth at ever-increasing speed, and maintain that beam coherence for a 10-minute burn. 100 gigawatts is a lot. The total electrical power consumption of the United States is around 400 gigawatts averaged over time. The Starshot laser, during its 10-minute burn, would draw a quarter of that consumption. The energy delivered to a single sail in a single burn is around 1 terajoule, the energy released by detonating about 250 tons of high explosive. That energy gets dumped onto a 4-meter sail. The sail has to absorb almost none of it, because absorption equals heating, and heating equals destruction. The sail has to reflect or transmit almost all of the incoming light, with absorption levels below a few parts per billion. No material humans have ever made achieves that level of optical perfection at the required wavelengths and at the required mass per area. The Starshot team has identified candidate materials, multi-layer dielectric stacks, specialized nanostructured polymers, but none have been manufactured at 4-meter scales. The acceleration imposed during the burn is roughly 10,000 g-forces. Every component of the Starship, the camera, the processor, the laser communicator, the power source, the navigation system, has to survive being subjected to 10,000, times its weight in inertial force repeatedly for 10 minutes. Conventional electronics fail at hundreds of G, much less 10,000. The sail itself has to survive. The pressure of 100 gigawatts of light, focused on 4 square meters, exerts force on the sail that has to be borne by a structure thinner than a virus. The sail material has to be strong enough to handle the pressure without tearing, light enough to keep the total mass low, reflective enough to absorb almost no heat, and stable. Enough to maintain its shape during the burn. The pointing requirement is also brutal. The laser array has to track the receding sail with an angular precision of nanoradians. As the sail accelerates from 0 to 20% the speed of light, the angular adjustment rate at the laser array changes continuously. The sail is also a small target, 4 meters across, at thousands of kilometers of distance by the end of the burn. Missing the sail by even a small fraction of a percent of beam diameter wastes the energy, and the beam fails. The phased array architecture is the solution to most of these problems. Instead of a single 100 gigawatt laser, Starshot uses many smaller lasers, possibly tens of millions of individual emitters, distributed across a desert site spanning kilometers. Each laser contributes a fraction of the total power. The phases of all the lasers are coordinated electronically so that their light combines coherently at the target, producing the equivalent of a single huge beam. The phased array has been demonstrated at small scales. Scaling it up to 100 gigawatts remains an open engineering problem. The cost of the laser array is the dominant cost of the Starshot project. Estimates run from $10 billion to $100 billion, depending on technology choices and timeline. The probes themselves are cheap by comparison. The acceleration phase ends 10 minutes after launch. Then the probe enters a 20-year coast through empty space. That coast turns out to be its own crisis, because empty space is not empty. Interstellar space is mostly vacuum. The density of matter between stars is about 1 hydrogen atom per cubic centimetre, with occasional clusters where the density rises. By terrestrial standards, this is the cleanest medium imaginable. By the standards of a spacecraft moving at 20% the speed of light, it is a sandstorm. A starship moving at 60,000 kilometers per second sweeps out a column of interstellar matter. Over a 25-year transit to Proxima B, that column is enormous. The probe encounters every atom and every dust grain along its path, at relative velocities much higher than any natural meteor. The kinetic energy of those collisions, even with tiny particles, is significant. The physics is straightforward. Kinetic energy goes as 1/2 mass times velocity squared. At 20% the speed of light, the velocity squared term is enormous. A dust grain of 1 microgram hitting the probe at 60,000 kilometers per second delivers an impact energy equivalent to detonating about 5 micrograms of high. Explosive at point-blank range. For a probe weighing a few grams total, that impact is catastrophic. Bigger grains are worse. A milligram-sized grain at the same velocity would vaporize the probe instantly and produce a small flash visible from Earth. A gram-sized grain, which exists as occasional pebble-scale debris, would deliver tens of kilojoules in a single impact, the same energy as a high-velocity rifle round. Concentrated on something the size of a postage stamp, the good news is that grains larger than micrograms are rare in interstellar space. The vast majority of the column the probe encounters is gas atoms and very small grains, which produce damage at the level of erosion rather than outright destruction. The probe's leading surface over 25 years will be slowly sandblasted by hydrogen and helium atoms hitting one at a time. The bad news is that even erosion adds up. Calculations by the Starshot team suggest that the leading edge of an unprotected sail would accumulate enough damage during transit to compromise the structure before arrival. Some kind of shielding is required. The shielding options are limited by the mass budget. The probe cannot carry significant armor without sacrificing the velocity that makes the mission possible. Proposed solutions include extremely thin coatings of high-density material on the leading surface, designed to absorb impacts without adding much mass, shaped designs that present a small cross-section in the direction of motion and, for the most pessimistic estimates, redundancy in the fleet itself, launch enough probes that some survive even with high attrition. The redundancy approach is the official Starshot plan. The mission profile assumes that a substantial fraction of the launched probes will be lost en route, primarily to dust collisions, and accepts this as a feature rather than a flaw. By launching 1,000 probes, the team can lose 900 and still have a successful mission with the remaining 100. The dust environment between Earth and Proxima Centauri has been characterized to first approximation by direct observations from interplanetary missions and indirect inferences from astronomical surveys. The actual transit conditions remain uncertain. The probe fleet may encounter localized clumps of dust that wipe out larger fractions of the swarm than current models predict. There may also be regions of unexpectedly clean space where attrition is lower than expected. This is the long crossing. 25 years of slow erosion, occasional catastrophic impacts, and steady navigation toward a target that is itself a moving point of starlight. Then comes the flyby, and the next problem. The Starship arrives at Proxima B 25 years after launch. It has 8 minutes of useful imaging time during the flyby, the window during which the planet is close enough for the camera to resolve features. After that, the probe is past the planet, accelerating away into the interstellar void on the far side of the system, never to return. In those 8 minutes, the camera takes pictures. The pictures fill the onboard memory. Then the probe has to send the data back to Earth. Earth is 25 light-years closer to the probe than Proxima Centauri is to Earth, because Earth is the destination of the data and Proxima Centauri is far. Wait. Let me restate. Earth and Proxima Centauri are 4.2 light-years apart. The probe is now at Proxima Centauri. The data has to travel 4.2 light-years back to Earth. The transmission time at the speed of light is 4.2 years. That is the irreducible delay. There is no way to make data arrive faster than light. The harder problem is the transmitter. The Starship is a centimetre-scale wafer with a few grams of total mass and access to whatever power its tiny power source can deliver. To send a useful signal across 4.2 light-years to a receiver on Earth, the probe needs to focus a beam tightly enough that a meaningful fraction of the energy actually reaches the receiver, and it needs to do this with hardware that fits on a chip. The best available solution is a small laser integrated into the Starship, firing pulses through a small lens system. The Starshot design proposals call for transmitter laser powers in the watt range, focused with a lens a few centimeters across. At Earth, the receiver would be the same phased array laser system that launched the probe, now operating in reverse as a telescope. The phased array, by virtue of its size, provides enormous collecting area for the faint return signal. The data rate is small. The transmitter is weak, the distance is enormous, and the receiver, even at its best, can only pull a limited number of bits out of the noise. Best estimates suggest the Starship can send back kilobytes per day during the post-flyby coast. A high-resolution image, even a single one, takes weeks to transmit. The full data set from an 8-minute imaging window might take months or years to download. This is acceptable. The data will arrive eventually, even if slowly. What matters is that the probe's 8 minutes of observation reach Earth at all. There are failure modes. The probe might survive the transit but be damaged enough that its laser cannot focus correctly. The camera might survive, but the memory might be corrupted by radiation. The aiming might be off, sending the laser into empty space rather than toward Earth. Each of these failures is silent. Earth simply never receives a signal, and the probe is presumed lost. The fleet redundancy strategy compensates again. With 100 probes arriving, even if many fail individually, the swarm produces enough independent attempts that a few should successfully transmit. The data from those few would be the most valuable photographs in the history of human science. The 8-minute imaging window itself, the moment when all of this engineering pays off, is the next waypoint. It is shorter and stranger than it sounds. The probe is moving at 60,000 kilometers per second. Proxima B at closest approach will be tens of thousands of kilometers away. The geometry of the flyby determines how long the camera has to do useful work, and the answer is short. Let the closest approach distance be 100,000 kilometers. The probe approaches Proxima B head-on, passes the planet, and recedes on the far side. The total path length where the planet appears as a meaningful target, large enough in the field of view to resolve continents and oceans, is a few million kilometers in length. Divide that by 60,000 kilometers per second, and you get a useful observation window of perhaps 8 to 12 minutes total. In that window, the camera has to do everything. It has to acquire the planet, lock on, autofocus, capture images at multiple wavelengths, store the data, and prepare to transmit. There is no time for second attempts. There is no opportunity to reposition. The flyby happens once, in real time, and whatever the camera captures is the entire scientific yield of the mission. The camera resolution depends on the chip's optical design. Starshot's proposals call for cameras around 20 megapixels, with optics tuned for the kind of resolution achievable from a centimetre-scale lens at 100,000 kilometre. Range. The expected ground resolution at closest approach is somewhere in the kilometre range. That is enough to see continents, to identify oceans, to detect cloud features, to image major surface variations between the day side and the night side. It is not enough to see cities, structures, or detailed surface morphology. The flyby trajectory matters enormously. A probe passing directly over the substellar point sees the day side at full illumination, but misses the terminator strip and the night side. A probe passing along the orbital plane sees both faces of the planet over the course of the flyby, but never sees either face perfectly illuminated. The choice of trajectory has to be made before launch, 25 years before the data arrives, and cannot be revised once the probe is on its way. The Starshot team has discussed the possibility of including some onboard navigation to allow the probe to adjust its trajectory during transit. This requires fuel, which requires mass, which compromises the velocity budget. The current consensus is that Starshot probes will be entirely passive, locked into whatever trajectory the launch laser sets. The fleet redundancy provides some hedge. Different probes, launched at different angles, will arrive on different trajectories, increasing the chance that at least one passes, through a scientifically valuable approach geometry. The other variable is timing. Proxima B's 11-day year means the probe's flyby will catch the planet at one specific phase of its orbit. From the probe's reference frame, the planet appears as a fast-moving point of light against the larger field of the star. The relative motion between probe and planet during the flyby is small. Both are moving fast, but together, so the camera does not have to track at extreme angular rates. The challenge is just being in the right place at the right moment. After the 8-minute window closes, the probe continues outward, past Proxima B, into the void on the far side of the Alpha Centauri system. It transmits its data home over the following months. Then, it falls silent. The next waypoint examines why the swarm strategy is essential, given everything that can go wrong. The Starshot architecture does not call for one probe, it calls for 1,000. The reason is the failure analysis at every stage of the mission profile, which yields uncomfortable success probabilities for any single probe. Acceleration phase failures might claim 10 to 30% of the launched fleet. Sails that tear, chips that overheat, alignment errors that send probes off course, all of these are statistical inevitabilities at the scale of mass production. 1,000 probes launched yields 700 to 900 that survive the burn intact and on trajectory. Transit failures from dust collisions might claim another 20 to 50% over the 25-year coast. The exact rate depends on the actual interstellar dust environment, which is uncertain. After transit, the surviving fleet might be 300 to 700 probes. Approach failures, probes that arrive but pass too far from Proxima B for useful imaging, or that arrive at trajectories that miss the planet's dayside, claim another large. Fraction, the targeting precision required to fly within 100,000 kilometers of the planet after 25 years of free coast, is extraordinary. Small errors in the launch velocity vector compound over the transit into large positional errors at arrival. Some probes miss by millions of kilometers. Imaging failures during the 8-minute flyby window, cameras that malfunction, memory that corrupts, processors that crash, claim another fraction. Of probes that arrive on viable trajectories, perhaps half achieve a usable observation. Communication failures, where the probe images successfully but cannot transmit the data home, claim a final fraction. Lasers that misfire, lenses that misalign, power systems that fail, all of these silently kill probes that otherwise succeeded. Accumulating all the failure modes, a single probe has a success probability somewhere between 1 and 10%. This is not an acceptable success rate for a single mission. It is a perfectly acceptable success rate for a fleet of thousands. The fleet strategy is also useful for a separate reason. Different probes can be optimized for different observations. Some probes can carry cameras tuned for visible light, others can carry infrared sensors, still others can carry magnetometers to measure the planet's magnetic field, or its absence. Spectrometers, polarimeters, particle detectors, each instrument adds mass, but no single probe has to carry everything. The fleet collectively carries the full instrument suite, distributed across many small probes. There is a cooperative imaging concept in some Starshot proposals where multiple probes time their flybys to provide coverage of the planet at different phases. One probe flies over the dayside, another flies over the terminator, a third flies over the night side. Together, the data streams reconstruct a comprehensive picture of Proxima B from multiple angles, multiple wavelengths, and multiple trajectories. This is the largest swarm spacecraft mission anyone has ever proposed. Coordinating 1,000 independent probes, each sending its own data stream back to Earth across light-year distances, requires ground infrastructure that has not been built. The downlink bandwidth alone, receiving simultaneous laser transmissions from hundreds of arriving probes, is a substantial engineering challenge. But the fleet strategy makes the mission possible at all. Without it, the failure modes accumulate to near certain mission loss. With it, the failure modes accumulate to a probabilistic guarantee that some data from some probes will eventually reach Earth. There is one alternative architecture that has been proposed, and it solves the engineering problems by accepting longer travel times. It is the next waypoint. The German physicist Claudius Grosz has proposed a different approach to interstellar exploration. Grosz's concept is called the Genesis Project, and it abandons the human timescale constraint that drives Starshot's extreme engineering choices. Instead, the Genesis probes travel slowly at around 4.6% the speed of light, less than a quarter of Starshot's target velocity, and accept transit times of approximately 90 years to reach Alpha Centauri. The slower velocity makes everything easier. The acceleration phase no longer requires 10,000 g-forces or 100 gigawatts of laser power. The dust environment causes less damage at lower relative velocities. The probes can be larger, carry more instruments, and survive longer transits. The communication systems can be more powerful. The trade is patience. A probe launched today arrives in 2120. The data starts coming back in 2124. No one alive at launch will see the results. Grosz's specific proposal goes further than just observation. The Genesis project envisions probes carrying biological cargo, packages of unicellular microbes, designed to be released onto worlds that are transiently habitable but currently lifeless. The idea is not exactly terraforming. It is seeding. drop microbes on a planet where conditions might allow them to survive and evolve, then let evolution take its course over geological time. This is a controversial idea. Astrobiologists worry about contamination of potentially native biology. Ethicists worry about the consequences of imposing terrestrial life on alien worlds. Engineers worry about the technical feasibility of keeping microbes alive for 90 years in interstellar space, then releasing them in a viable state. Gross's response to these concerns is that worlds like Proxima B, currently sterile, hostile to surface life, but possibly capable of supporting biology under the right conditions, might benefit from a kickstart. If the planet can support life but has not produced any, seeding it with terrestrial microbes might initiate a biosphere where none currently exists. The Genesis architecture also includes a clever maneuver for slowing the probe at arrival. Rather than flying past the target system at 90 years worth of cruise velocity, the probes would use the Alpha Centauri stars themselves as brakes. The proposal involves Alpha Centauri A's light pressure decelerating the sail, then Alpha Centauri B providing a gravitational redirect, finally bringing the probe to A. Manageable velocity at Proxima Centauri after another 46 years. The total transit time, including the deceleration sequence, is around 140 years. That is longer than Starshot's 25, but the probes arrive in orbit rather than as a flyby. An orbital probe can do detailed science indefinitely. It can map the planet at high resolution. It can return data over decades. It can deliver cargo to the surface. Whether the Genesis project's biological mission is desirable is a separate question. The architecture itself, slower and more capable, represents a genuine alternative to Starshot's high-speed flyby model. Different missions might use Genesis-style probes for some targets and Starshot-style probes for others, depending on what each system requires. For Proxima B specifically, the choice between flyby and orbital science is the choice between a single 8-minute look and decades of detailed observation. The 8-minute look is achievable in 25 years. The decades of observation are achievable in 140. Both options remain on the drawing board. Neither has launched. The infrastructure required for either does not yet exist. The final waypoint is the verdict. What does Proxima B actually teach us about every red dwarf world? Proxima B is not the friendly Earth twin that the press releases of August 2016 suggested. It is a planet sitting 4.5 million miles from a flare star, tidally locked into permanent day and permanent night, almost certainly without a meaningful magnetic field, possibly without a significant atmosphere, and exposed to ultraviolet doses that exceed the lethal threshold for the toughest microbes in our biosphere. The mission planners now plan around these facts. The probes being designed for the trip will arrive expecting a hostile target. They will image whatever they find. The most likely findings are some combination of bare rock, frozen nightside ice deposits, possibly a thin residual atmosphere held together by ongoing volcanic outgassing, and, possibly, though less likely, a substellar pool of liquid water surrounded by frozen wasteland. The deeper lesson is not specifically about Proxima B. It is about red dwarf habitability in general. The galaxy is dominated by red dwarfs. Around 75% of all stars are M-class. If habitable planets are common around red dwarfs, the galaxy is full of life. If habitable planets are rare around red dwarfs, life requires bigger, calmer stars, and the available real estate shrinks dramatically. Every problem identified for Proxima B applies to every red dwarf system. The flare problem is universal among M-class stars. The tidal locking problem is universal for habitable zone planets in tight orbits. The atmospheric stripping problem is universal for any planet that close to a fully convective star. The youth phase atmospheric loss problem is universal across the whole class. This does not mean every red dwarf planet is dead. It means every red dwarf planet faces the same set of challenges as Proxima B, with magnitudes that vary based on the specific star and the specific planet. The TRAPPIST-1 planets face similar issues. The Teegarden star planets face similar issues. Every red dwarf habitable zone candidate ever discovered sits inside the same envelope of stellar threats. The optimistic case for red dwarfs holds that life is tougher than we estimate. The DNA-based biology that fills Earth's biosphere is one specific solution to the chemistry problem. Other solutions might use different molecular bases, different repair mechanisms, different shielding strategies. A planet could be hostile to terrestrial-style life and friendly to alternatives we have not encountered. The pessimistic case holds that life requires conditions much closer to Earth's than the current habitable zone definition admits. Stars like our home star, calmer, less violent, with stable magnetic fields and modest flare rates, would be the only places where biology has the centuries of consistent conditions needed to evolve and persist. The data from Proxima B, when it arrives, will answer this question for one specific planet. The answer for that one planet will inform our estimates for the millions of similar planets around similar stars throughout the galaxy. If Proxima B is dead, that is one data point. The next nearest red dwarf planet is a few light years farther, and the question becomes whether to build a second laser array, launch a second fleet, and ask the question again. If Proxima B is alive, even at the level of subsurface microbial mats in an under-ice ocean, that is the most important biological discovery in human history. Every other red dwarf system becomes a candidate. Every estimate of life in the galaxy gets revised upward. The Drake equation, which has haunted astronomers for 60 years, gets a new term filled in. Either way, the answer will arrive. The probe is being designed. The laser array is being engineered. The funding is being raised. Sometime in the second half of this century, if the engineering holds and the budgets survive, a few grams of silicon will scream past Proxima B at 60,000 kilometers per second, take 8 minutes of pictures, and send the photographs home across 4 years of empty space. We will see the closest exoplanet with our own eyes. The verdict will be in the data. End of mission briefing.